Okay. Um, so hi everyone. So today we're going to talk about um, inferential statistics. Okay. So before we get into all the important concepts related to this topic, let's just start with an example of why this matters and what all this tells us. So let's say I wanted to see if people who sit on the left side of the classroom or the right side of the classroom, which one of those has better memory. Okay. Um, that would obviously be correlational, but or quasi-experimental, but doesn't really matter. It's just an example. There's really no reason to expect an effect here, right? This is just a case where there should be no difference between people who choose to sit on the left and people who choose to sit on the right. Okay, it should be what we call a null effect, meaning there's no true difference there. So I split people up. Um, have the people that sit on the left of center do a memory test, and the people on the right of center do a memory test. And then I compare the means of each group. Well, think about it for a second. Are these two, even though we wouldn't actually expect a difference, wouldn't actually expect sitting on the left versus the right side of the classroom to matter, will the means come out the same? Think about that for a second. Will the means be identical? No, they actually won't. Chances are, I mean, it's possible, but rather it's more likely that there'll be a very slight difference in the means between the two groups, despite there being no actual effect, no real difference between people who sit on the left and people who sit on the right side of classrooms. But when we draw a sample, even though it's random, it's not going to be perfect, right? It's going to still be off by a little bit. So that's kind of the premise behind inferential stats. We want to know when we see a difference between means, or really whatever kind of observation we make, is it actually a meaningful difference? Is it enough to claim that, yeah, there's something there? Yes, our manipulation did something. Yes, there's a significant correlation, or all these other things. Um, we need to kind of tease that apart from just due to randomness, due to individual differences, which we'll get into. Did we see a small difference there, or was that difference because of our effect, or was it just because of randomness and individual differences and extraneous variables? Okay. So again, we're not going to see an effect here, or we shouldn't, but that doesn't mean the means are going to be exactly the same. Maybe just the particular sample we have, people on the right tried a little bit harder, paid a little bit more attention, whatever it might be. That might result in the right side of the class remembering slightly more information than the left side of the class. But again, that's what we're trying to tease apart. Is it just that? Is it these minor individual differences, these extraneous variables, or is it actually a difference in the population? Did our manipulation or our variable actually have an effect that isn't just randomness? So with that in mind, today we're going to talk about some of the concepts in inferential stats. We'll start from the ground up. Sample mean versus population mean, sampling error, sampling distribution of the mean, standard error, and degrees of freedom. Okay. So just a reminder, a couple key terms here. Remember frequency distribution. This is just like a histogram, seeing how frequently each score is. Okay, and we'll see examples, don't worry. And then variance and standard deviation are measures of change. So how much do the scores vary from the mean? Okay. So we kind of talked about these first two parts, creating a hypothesis, where you're phrasing it as a comparison between two conditions or more than two conditions, and comparing the means of the dependent variable for each level of the independent variable. Okay, so now we're going to talk about the next step, which is to perform, after you've collected your data, performing stats to see if the difference is actually meaningful. Okay, so again, when we think about comparing the two means, or more than, or even more than two means between conditions, they're not going to come out exactly the same. And this is because there are sources of variability would be other than any effect we caused. So the general assumption is that scores can vary in several different ways. One is due to our independent variable, due to our manipulation. So if we see a difference between conditions, between say cell phones and in the driving simulator and no cell phones in the driving simulator, that of course could be because of our manipulation of giving them a cell phone or a quasi-experimental variable. So if I wanted to compare something I couldn't manipulate, the same logic applies, right? Could be that that variable I'm splitting people up by is actually meaningful and it's associated. Remember, it's associated with not causing a difference. We can't say that because we didn't manipulate it. But it could be that that variable is actually associated with differences in some metric. However, while those certainly could be the case, again, extraneous variables could also contribute to differences. So it could be something like the testing condition, maybe the time of day you test them, or if they're a distraction. Individual differences is usually the biggest one. So if we compare, we run an experiment to see, do cell phones again cause more errors while you're driving? Do that in a driving simulator. Even regardless of that manipulation, some people are going to make more errors than others, right? It's not going to be the case that everyone makes the same amount of errors, regardless of, or independent of whether there's a manipulation there, right? Some people are just better or worse drivers than others. So, kind of at the basic level, again, remember that your interest is in the population. It's about what does your research actually say about the population of interest. So I might be interested in, again, cell phones and driving. If I'm interested in applying that to everyone who owns a cell phone and drives, well, that's my population. Everyone who owns a cell phone and drives. But of course, we can't test every individual that has a cell phone and drives because that's obviously too many people. Remember, we have to take a sample. We have to take a subset of that population to test our effects on. Okay. So if my population was hypothetically 500 or 200 people rather, and you took samples of 5, you could get quite a few different samples from that population of 200. I could be wrong on this, but I think it's about 2 billion. It seems pretty high, but um, bottom line is that drawing randomly from a population to get your sample, you can get quite a bit of difference in what you draw. It's random. Okay. So you can do this if you want, but it's pretty straightforward. If you were to select a sample of 5 people from a population of 200 values, like we have here, what do you think the sample mean would be? So here's our population. Okay, this is everyone that we're interested in. applying the research to. Notice the mean is 20.13. So yeah, go ahead and do that. Just pause the video, draw some numbers from here, 5 numbers from here, and see what your sample mean is. Not your population mean, but your sample mean. So the mean of the 5 that you pick randomly. Okay. By the way, remember this is a histogram, so this is just a plot of how frequent each score is. So you notice we have, I don't know, like 2 people got 5, 2 people got 38, a lot of people got 19, so on and so on. Okay. Now, if you did that activity, you should have found that your sample mean was not equal to the population, right? Chances are very high, although it's not impossible, that the 5 people you drew did not have the same mean as this whole population. The mean was not 20.3. Most of you probably got something close to that. Maybe you got 19, maybe you got 21, 22, somewhere in that range. Less of you probably got something like, say, 11 or 33. Well, that's kind of the premise again behind why samples can differ and not reflect the population, and also why we see differences even when our manipulation did nothing. So the population only has one mean, like we saw here. It was 20.13. However, each sample you take from that population is going to have a mean of its own, and they're going to be different. So in a perfect world, if we drew 5 people from here, we would get the same mean as the population. But in reality, that's not what happens. Because it's randomly selected, sometimes we'll get very close to the actual population mean, sometimes we'll get a little bit further, and sometimes we'll get quite a bit further. Every sample you take will have a different mean. And again, some sample means are close to the population, whereas others are going to be far away from it. Now, again, we want our sample mean to be as close as it can be to the actual population. But this, of course, varies. So you can have what's called a small sampling error, or you can have what's called a large sampling error. So small sampling error is, again, kind of like I said, just a little bit off of the true population mean, something like 21 or 19 or 19. However, you might get a large sampling error and get something like 12 or 30, much farther away from the actual population. Okay? So keep all this in mind, and this is going to again illustrate how we end up with different errors in statistics and what our statistics are going to show us. Okay, now we would do this if we're meeting in person, but we can actually plot the sample means in a frequency distribution. So remember that this is a histogram again, and we can do the same thing for our sample means. So if we were to draw, say, like 200 different times, 300 different times, take five scores at random, and get all those different sample means. So say 300 different sample means drawn from this population. Well, we could plot those just like we plotted the scores here. We can plot our sample means in a histogram. And what that'll give us is a sampling distribution of the mean. And this is just a frequency distribution of the means of every possible sample taken from a population. Or that would be rather if you did it like an infinite amount of times, or as many times as possible, or you could possibly do it just a limited number of times. But just like how we plot the raw scores here, we could plot the means of each of our samples that from this population. Okay. And chances are what's going to happen is it's going to form a normal distribution. Okay. More on that next. Or rather, actually, I'll talk about that now. Typically, we find that when we draw samples, just due to probability, it forms a normal distribution. Hopefully, remember what a normal distribution is, but this is just that bell curve shape in a histogram. So again, looking at this, this is almost a normal distribution. Remember, a normal distribution is when you have the most common scores are clustered around the mean. Okay. So let's say we had, using a different thing, say we're talking about height. Chances are, I don't know this for a fact, but pretty certain, seems like a reasonable assumption that if the height average in the world is say 5'10", 5'10" is also going to be the most commonly occurring height, right? 5'11" is going to be also commonly occurring because it's very close to the mean, right? That's not always the case. You can have the mean be different from the mode. If it's not a normal distribution, you can have you can have a mean that's not the most frequently occurring value. But when you have a normal distribution, remember that is the case. So when it forms this kind of bell curve shape here, typically, or at least pretty close, it's pretty close to the fact that whatever our mean is, that's also the most common value. And the further away you get from that mean, the less common the values are, which is again what you see here, although it's not perfect. So if we go over here a bit, we're a bit further away from the mean at 27. Well, those are also going to be less frequently occurring values. If we go way over here to say 37 or 38, those are going to be even less common because they're even further away from the mean. So just as a refresher, that's the premise behind a normal distribution. The further away you get from the mean, the less frequently you're going to see those values. The closer to the mean, the more frequent that score. Okay, so just again looks like this kind of a bell curve here, but this one is not perfect. Well, generally, when we draw samples from a population, we get a normal distribution. So, in other words, sample means are more likely to be close to the population mean than to be farther away from it. So, think about that for a second. Actually, I'll just put that back on screen for a second. Sample means are more likely to be close to the population mean than to be far away from it. Actually, we'll take a break there. So I'd like to add an illustration to that.